So we looked at finding powers of complex numbers in polar form from de Moivre's theorem. Now we're going to look at the nth root theorem. And this is something I think is really cool, and I like teaching this. Some people skip it, but I think it's a valuable part of trigonometry. So the nth root theorem, to find the nth root of a complex number in polar form, use the formula given by z to the 1 over n, so that means an nth root, is r to the 1 over n, and then times its cosine of theta over n plus 2k pi over n. So this generates several different solutions. And so k is going to be, you go with it 0 first, then 1, and then 2, then 3, until you get to n minus 1. So if you're talking about a fourth root, you'll do k being 0, 1, 2, and 3. If you're talking like a fifth root, it'd be 0, 1, 2, 3, 4. If you're talking about a square root, it's going to be k 0 and 1. And this formula, generates your k's. So evaluate the cube roots of z equals 8 cosine of 2 pi over 3 plus I sine of 2 pi over 3. So for this, if we're looking at z to the 1, which would start working when asked it to, z to the 1/3, it's going to be 8 to the 1/3 times cosine of, now it's going to be, that was theta over n, so theta over n. So 2 pi over 3 over n, which is 3, plus 2 pi k over 3. And I'm going to go through the k's being different values. Plus I sine of 2 pi over 3 over 3 plus 2 pi k over 3. So we'll look at three things: k being 0, k being 1, and k being 2. So for k being 0, our z to the 1/3, one of the three roots, it's going to be 8 to the 1/3 is 2, times cosine 2 times pi over 3 is 2 pi over 9, plus that's 2 times pi times 0 over 3, plus I sine of 2 pi over 9, plus 2 times pi times 0 over 3. So let me give myself a little more space to work here. So I want to restate this. Our first root is z to the 1/3 of z to the 1/3 is going to be 2 times cosine of just 2 pi over 9 plus I sine of 2 pi over 9. Our second one, we have k equals 1. We have z to the 1/3 is going to be 2 times cosine of 2 pi over 9 plus 2 times pi times 1 over 3 plus I sine of 2 times pi times 1 over, forgot the 2 pi over 9 far apart. 2 pi over 9 plus 2 times pi times 1 over 3. So we end up with z to the 1/3 is 2 times cosine of, now to get these to have a common denominator, I need to multiply by 3 over 3. So 2 times pi times 3 is 6. 6 pi plus 2 pi is 8 pi over 9 plus I sine of 8 pi over 9. Okay, moving on to, make sure I get my parentheses in order. The last one, k equals 2. So our z to the 1/3 is going to be 2 times cosine of 2 pi over 9 plus 2 times pi times 2 over 3. And again, to have the same denominator, we'll multiply by 3 over 3. Plus I sine of 2 pi over 9. Sorry about the phone ringing. So I sine of 2 pi over 9 plus 2 times pi times 2 over 3. And again, we'll multiply by 3 over 3 to get the common denominator. So we have z to the 1/3 equals 2 times, and then we have cosine of, that's 2 pi over 9. So 2 pi times 2 is 4 pi times 3, 12 pi. 12 pi plus 2 pi would be 14 pi over 9. Plus I sine of 14 pi over 9. And that is our process. So, hope that makes sense. Kind of a neat idea is that you can take cube roots, square roots, and so on of complex numbers. And this is what it looks like. And you can graph them if you, to give you another picture of it, but graphing them, well, in the first case, maybe we'll just graph it for fun. So in all of them, the radius is 2. And in the first case, it's 2 pi over 9. So 2 pi over 9 is short of pi over 3. So let's say it's going to be out, if this is 2, so somewhere around here. Then 8 pi over 9 is the second one. That's just short of being at pi. So what do we say? So somewhere about here. And the third one was 14 pi over 9. So 18 pi over 9 is 2 pi. And 12 pi over 9 would be 4 pi over 3. So we're looking at something probably around here. So we see where we're getting these angles, or where we're getting these solutions on a complex plane. So, or these roots on the complex plane. Anyway, kind of a fun process, and it hopefully it's meaningful for you, because I think it's really kind of pulls together all these concepts of math. Well, not all, but it helps to pull together some of the math. Okay.